Okay, oh, that'll help. Okay, so I think we're all set to get started. Thanks for coming in today. It would have been really depressing if it was an empty room. I hope you guys can stay for the whole marathon session today, 2 lectures. Any questions before we get started from last lecture? General questions? Okay, and let me just give a note to the people who will be watching this on tape. If you're seeing this on tape, that means homework is due, and the reader will be coming in to pick up the homework. Okay, there's a question?
For homework, do we need to include all the resistance for hand calculation?
You know, I talked to Al Molnar, and he informed me that he was very concerned about the homework because he found that he thought the problems that he'd written were very open-ended. And he apologized, and I said, that's okay, you know, we'll give the benefit of the doubt to the students. So the reader is going to get prepped on homework number 1 to grade it very flexibly because there's multiple ways to interpret the problem. So you shouldn't worry too much about that. Okay, any other questions or comments? All right, so let's recap where we were, and let's try to define the problem again as we did last lecture. So the problem that we posed last lecture was we have a generic 2-port that could represent a single amplifier or a chain of transistors, multi-stage amplifier. And we asked the simple question, what are the optimal source and load admittances such that we can transfer the maximum power to the load? In other words, we maximize the power gain of the system. And the observation from last lecture was, well, the maximum power that you can transfer from the source is the power available from the source, from the maximum power transfer theorem. And so if we look at the transducer gain is the power flowing into the load divided by the power available from the source. And we derived last lecture that this is a function of both the source and load admittance and the 2-port parameters of our network. So it should be pretty clear that in order to maximize the power to the load, what we should do in turn is first of all maximize the power, basically to try to make the power going to the load equal to the power available from the network. So from the load's perspective, if we could design the load so that it represented a complex conjugate admittance to the 2-port, then we know we'd be extracting the most power possible from the 2-port. So that's the problem we need to solve from the load side. From the source side, it's the same thing, right? We want to get as much of the available power into our 2-port. And to do that, we simply make the input admittance. We'd like Y source to be the complex conjugate of the input admittance. So the intuitive result is simply make Ys Y in star and YL Y out star. And this should give us GT max. Any questions about the intuition leading to that conclusion? And you'll note that in general, because Y in and Y out are a function of Y, each one is a function of both Ys and YL, this is a pair of equations that we can simultaneously solve. So if we simultaneously solve, let's call this equation 1 and equation 2, 1 and 2 for Ys, YL, then we can find GT max, Ys opt, and YL opt. So whenever you have 2 equations and 2 unknowns, you first have to ask, is there even a solution? So we're kind of assuming the solution exists. Intuitively, we can say, yeah, it seems like the solution should exist. But can anyone think of conditions where there might not actually be a solution. So let me pose that question. Does the solution exist? Is it unique? Okay.
Well, I think it's not necessary that a solution exists. For example, if the input resistance is at the same time the output resistance of the two-port, then we're not necessarily able to match it exactly without any further matching network with the input and the output resistance at the same time.
Okay, so let's say we have this two-port, and we found out that we have to provide a biconjugate match, right? So that I think what you said is that no, not necessarily, that the unique solution or a solution might not exist. Well, you're right. Actually, the solution does not always exist, but I'm looking for something, a different insight into why the solution might not exist. Okay, so the solution might not exist so it turns out that the solution might not exist, should write this down, might not exist if two-port becomes unstable. Okay, and we haven't really talked about stability at this point, but just intuitively, if I present a certain YL here that causes the output to oscillate, then clearly this solution for maximizing the power gain, transducer gain, does not exist. In fact, if the two-port oscillates, that implies infinite power gain. In other words, I might actually just short the input. So that means that Pin is equal to 0, and yet I could have Pout not equal to 0. That means that the two ports are actually oscillating and in effect generating infinite power gain. So it'll be when we derive the expressions for GT max, we'll find the conditions, we'll actually find a mathematical condition that says, yeah, this condition has to be satisfied, and it'll turn out, we'll show later on, that that condition is equivalent to the condition for stability. So if the two-port is not stable, then if the two-port is not unconditionally stable, then there are cases where there is no maximum gain. And for those cases, we'll come back and define another form of gain. So this is just looking ahead. I don't want to make this too confusing, just a preview. Okay, so let's go back to where we stopped last lecture. Last lecture, we were comparing the various power gains. And what we did is we first of all showed that the transducer gain, which is a function of both Ys and Yl, we first of all showed that this is always less than or equal to the available gain. And the available gain is only a function of Yl, and is that right? Let me just double check. Available gain is power available from the two-port divided by power available from the source. So it should only be a function of Ys. Okay? And we found that equality only happens when Ys is equal to, so equality for Ys equal to Yin conjugate. Similarly, we found last lecture that GT, again a function of Ys and Yl, is always less than or equal to the power gain. The power gain is only a function of Yl. It's the power in the load divided by the power coming into the network. And again, equality for Yl equals to Yout conjugate. So it's actually now pretty clear that if we simultaneously match the input and output, so biconjugate match, again, same thing from last slide, same concept, then we have GT max, the maximum obtainable gain as a function of the source and load, and it's equal to GA max, and it's equal to GP max. Okay? So our intuition is right. So you can see now why we spent so much time defining these various gains, because it gave us a nice way to understand how to maximize the transducer gain. Okay? Now, there's actually several recipes for a biconjugate match, several ways of going about to calculate this. The most straightforward approach is to say, okay, I know what Y in is for a two-port. It's Y11 minus Y12 Y21 divided by YL plus Y22. And I simply set that equal to YS star. So this is our first equation, from same as the one that we wrote a few slides ago. And likewise Y out, which is Y22 minus Y12 Y21 YS plus Y11, and we set that equal to YL complex conjugate. Now, even though this is only two equations, it's really four real equations, because these are complex quantities, and we can solve for the unknowns YS opt, real imaginary part, YL opt, real imaginary part. Okay? And you can do that, actually, and what you'll find is that several pages of algebra, several, let's say, painful pages of algebra, and when you're solving the equations, you'll run it into the condition, you'll have a square root somewhere, and you'll say, oh, the square root has to be positive, and then that'll give you the condition under which the solution exists, and that's exactly the condition that we were talking about that could lead to oscillation if it's not satisfied. Okay, so this is one procedure for finding YS and YL. Can someone think of maybe another procedure that might be easier? Now think about exactly. So the comment from the class is take derivatives, right? You have a function, you want to maximize it. Let's look at its variation. Find the point where the variation is equal to 0, and that should be the optimal point. Very good. So for instance, if I take the derivative, so let me say YS is GS plus JBS, YL is GL plus JBL. Then if I take derivative of GT with respect to these four quantities and solve them, then I can also get the solution. But that's also four equations, right? What have I really gained by doing this? So is this better? Not really. It's still four equations that I have to solve. Okay? So we'll call this approach 2. And we'll call this approach 1. All right, can someone think of a better way of doing this? Maybe that involves fewer equations. Okay, well, a third approach is to realize that when GT is maximized, it's actually equal to GA, and it's also equal to GP. And GA and GP are only a function of one admittance. So in effect, they're only a function of two variables. So I could take derivative of GA with respect to the source. That's two equations. Or I can also equivalently take with respect to GP. And that's also two equations. So that's actually the better route to take, because you only have to solve two equations. And when you're done, so for instance, if I solve for GS opt and BS opt from these two equations, I can find YL opt by simply making YL equal to Y out star. And Y out, remember, is a function of YS, And so this is a recipe for finding the optimal load. So even though this only gives us the optimum source, with one line of algebra we can find the optimum load as well. And here, ys opt we can find by doing the same thing. Okay? Any questions about that? Does that make sense? Good. All right. So now we have a nice recipe for doing a simultaneous biconjugate match. Before we go into the gory details, let's solve a simpler problem just to see, basically just to get some intuition for the solution. So let's look at a unilateral two-port. So for a unilateral two-port, y12 is equal to 0. That means that y in is simply y11. And y out is simply y22. So it's trivial, right? To get a complex conjugate input and output match, I simply make ys y11 conjugate and yl y22 conjugate. Make sense? Very simple. So now, going back to the condition of stability, under what conditions does a solution exist here for optimal source and load? Is it for any two-port, for an arbitrary two-port? Anybody want to guess? Well, think about stability again. If the device... I'm sorry? Very good. If the device has a negative real part, that's actually unphysical. I can't put a passive source admittance that's the complex conjugate of that, right? I can generate a negative conductance, but that requires another amplifier, and that's not really the problem we're solving. The problem we're solving is we're looking for a passive source and load termination to give us the maximum gain. Well, let's take an example. Let's take the example that we used for a simple transistor model that's unilateral. Well, if I look into the input here, the input admittance is just this in series with this, right? And so if I want to drive it with a complex conjugate admittance, I just put an inductor here. If this is Rg, I drive it with Rs equal to Rg, and I make L resonate with C. And so now the input is a complex conjugate match. I can extract the optimal power from the source. And then on the load side, I do the exact same thing. I put an inductor here to resonate with this C, and I put an RL equal to RO to extract the maximum power from the output network. So these are the optimal source and load admittances. Okay, and as you see, they form natural. This one forms a series resonant network. This one forms a nice parallel resonant network, what we studied a couple lectures ago. And so once we have a resonant network, of course, you know that this condition for optimality is only obtained at one frequency exactly, at resonance. And so we want to make sure the input resonant frequency is equal to the output resonant frequency. And you'll also note that if you just design a circuit this way, you have no control over the Q. The quality factor is already set by the input admittance quality factor, right? So if I can't control the Q of the input and output, I just get what I get. And so what I'll find is that this optimality condition holds over a bandwidth which is, determined by the quality factor of my circuit. So I have optimal source and load over the bandwidth. So on the order, so when I say over, I mean approximately over this bandwidth. I have a good input and output match, and therefore I have maximum power gain. All right? Questions about that? It's actually interesting to calculate now how much power we get in this case. So let's do that. Let's just find how much power we can extract from this transistor. So power available from the source is Vs squared over 8 Rs. In this case, Rs is equal to Rg, right? And the power going to the load, let's say, is, I'll do it in steps. Let's say it's IL squared 1/2 times RL, which is in this case RO. Okay? So let's find IL. Well, in resonance, there's a circulating current flowing between the L and the C, and so this current by this GM generator all flows into the real resistances at resonance. So half of it flows here, half of it flows here. So we can say that the output current is 1/2 GM times V in. Okay? So now we need to find V in. Well, V in, it's a series resonant network. So V in, which is here, is equal to this voltage divided by this series RLC impedance. Well, again, at resonance, this cancels out with this. So V in is this current flowing in this loop. I in, which is simply Vs divided by 2Rg times this reactance. So V in is Vs divided by 2Rg, that's the current, times 1 over j omega CGS. Okay? That clear? Good. So now we have an expression we can plug in here. So this is 1/4 Vs over Rg Gm over j omega CGS times V in. And so the load, I could write that as 1/4. This is not there anymore. 1/4, let's say 1 over Rg, 1 over j, Gm over CGS over omega times Vs. And of course we recognize Gm over CGS to be the omega t of the device. Okay? So let's substitute that into the load. So I just take IL squared. So power to the load is 1/2 IL squared. So I have 1/16 1 over Rg squared. And I'm taking magnitude, so j goes away. Omega t over omega squared, Vs squared. And if I now divide this by power available from the source, that's Vs squared over 8Rg. And so the Vs squared cancels out. This 8 cancels out with this, and I get a factor of 2 here. This Rg cancels out with this Rg. And so my final expression looks like 1/4. Oh, and I forgot to multiply by Ro here. 1/4 Ro over Rg omega t over omega squared. If I made a mistake, maybe you guys can catch it. And this is basically the maximum gain I can get out of this device, assuming Ro is bigger than 0 and Rg is bigger than 0. And we know that to be physically true, right? That's actually interesting. Remember, Ro is not a physical resistance. Ro is the output impedance of our device. So for instance, if we look at our curves, if this slope is positive, that means that Ro is positive. But what if you had a weird kink in your curve, right? At this point, Ro goes negative, and that means that actually GT max, as we've defined it, doesn't exist. Because the device, under certain conditions, you can make the device oscillate in this region. Okay? We'll have a lot more to say about that later on. Okay, this is actually a really nice result. It tells me that the maximum gain I can get out of my device is a ratio of the omega t of the device divided by the omega of the device, divided by the frequency of operation. And then it's also determined by the ratio of the output resistance to the gate resistance. And remember, at the very first lecture I said if you don't have gate resistance, you don't have a physical MOS model. And that's because if there were no gate resistance, power gain would be infinite, right? And we didn't need to do all this analysis. If I don't have gate resistance, then the power, the average power P in is always equal to 0, because this is a capacitor and it only stores reactive energy. And so simple MOSFET model like this predicts infinite power gain. So RG is very important because it determines how much power gain you can actually get out of a device. And if you can be clever about the way you lay out your device in order to minimize RG, for instance, you can dramatically improve the power gain of your device. So let me give you a quick example of that. So layout dependence of power gain. So let's say you have a FET and you lay it out like this. So this is the gate, this is the source, this is the drain. And remember, our gate has two contributions. So our gate has our poly plus our channel. Now the poly resistance is quite easy to understand. It's just the resistance, it's proportional to the resistance of this gate finger, right? So usually when you design a transistor, someone will tell you, yeah, this poly is silicided and it has such and such sheet resistance, right? And of course you want to get the one that has the lowest sheet resistance. So you just calculate the physical resistance of this, and that contributes to this term. Now it turns out that this is actually a distributed structure because the current that goes into the gate doesn't all flow to here, right? The boundary condition is actually the current. So if I have I gate coming in, here I gate is 0 because I have current going down vertically into my device. So if I were to look at the current profile across this device, if I were to plot I gate from, let's say, x equals 0 to x equals w, then I would expect to see some profile like that. In fact, if this is a high quality circuit, it looks very linear. So we can say that it's almost linear. Now if you calculate the power loss to this piece of wire, this polysilicon, if you put in a linear current like this, you'll verify that the power loss goes like 1/3 of Ig squared times R. So the power dissipated in Rg is 1/3 I gate squared Rg. In other words, Rg poly, let's say. In other words, R poly is 1/3 R gate poly. Let's call this physical. Again, sorry about the notation. So this is the actual physical resistance of this, assuming you put current in uniformly. In other words, R gate poly physical is W over L times the sheet resistance. Okay? Clear? Now this term is a little bit more tricky. This is the induced channel resistance, and it's proportional to the resistance of the actual device. It turns out that because the channel, the gate current flows into the channel and then it flows into the source and drain, because the channel is resistive, that actually contributes a resistive part into the input admittance. And to actually analyze that problem is quite complicated. Intuitively, you would say that this should be proportional to the channel resistance. So if I go in there and look at VDS sat divided by IDS, that's roughly the channel resistance, and so this term should be proportional to that channel resistance. We'll come back to that. Let's focus on this term. So because this term is bias dependent, I can always bias my device to have a higher and higher current and lower channel resistance, and so I can eventually be dominated by just this term here. And this term, of course, does not depend on bias. So one way to minimize our gate is to use a multi-finger layout. In other words, instead of doing a device like this, I can lay out my device like this. And this is a standard trick in IC layout that you probably are familiar with. So here, if I have source and drain, over here I'm going to have source, drain, source, drain, source. And so I need to connect my sources together with some interconnect, and likewise my drain together. So this is my drain junction, this is my source junction, and this is my gate. And you can see this has a twofold improvement, because not only am I reducing my gate length by n, so if I have n fingers, so our gate goes down proportional to the number of fingers, but since these are now in parallel, I get another factor improvement. So our gate goes down like n fingers squared. So this layout is much superior to this layout. So first thing you do when you do high frequency layout is you go in and make all your transistors multi-finger devices to make them nice and low gate resistance. Okay. Questions? Okay, so let's look back at this expression that we derived for the gain, and let's ask an interesting question. What's the maximum frequency I can operate at and still obtain power gain for my device? Okay? We can see now that if I copy this expression, let me find the frequency where this is equal to 1. And again, copying this expression, it's 1/4 Rho over Rg omega t over omega squared. And let me call that frequency omega max. So omega max is the frequency where the power gain is equal to 1. And that in some way is a very nice metric. It tells me that if I go beyond this frequency, I can't get power gain from my device. In other words, the whole point of a two-port is to provide power gain. And if you can't get power gain out of your device, it's no longer acting like an active device. It's acting more like a passive device. And so this is a very important frequency. We'll find that it's related to omega t, but it's not equal to omega t. Okay? So in fact, it's very simple. I can now solve for omega max squared is equal to 1/4 Rho over Rg omega t squared. So if I take square root, I have that F max is equal to 1/2 square root of Rho over Rg times the Ft of the device. So under the simple approximation that we made, unilateral device, we can see that as long as I can maximize the ratio of the output impedance of the device to the gate resistance, I can go up to really high frequencies. And you can see in particular, you can even go higher than Ft. So whereas Ft characterizes the bandwidth of a wideband system and an RF system and a narrowband system, Ft is not that relevant because I can always tune out my parasitics. But I can't do that at an arbitrary frequency. Remember a couple lectures back we said, why can't you arbitrarily tune out parasitics at a terahertz or 10 terahertz or a billion terahertz for that matter? And that's because you won't get power gain out of your device. You can do it. Actually, it turns out it's really hard to design inductors and capacitors of those frequencies, but in theory you could, but you just wouldn't get power gain out of your device. Your device would be useless. It would just be a passive device. It would be providing no power gain. Okay. Questions or comments about that? All right, so this was a little bit of a diversion. Let's get back on track. So let's go back to the power gain, the general case, the power gain derivation. And we're going to take the approach of going after the load. So what we're going to do is we're going to take GP dBL equal to 0 and dGP dGL equal to 0. And, you know, I respect you guys. I know you guys can do algebra, so I'm not going to bore you to death. But what I'll do is give you the final answer. So let me define a couple of useful things. Let me define the product of y12, y21 as P plus JQ, or some magnitude L e to the J phi, where phi is the phase of this product. If I do that, then BL opt turns out to be Q over 2 M11 minus N22. I need to define M11 and M22. So basically I'm defining YJK as real part MJK plus J NJK. Okay? So this is the solution for the optimum load. This is the imaginary part of the optimum admittance, and the real part of the optimum admittance is given by 1 over 2 M11 square root 2 M11 M22 minus P squared minus L squared. And this gives us a maximum gain, which is equal to y21 squared magnitude divided by 2 M11 M22 minus P plus square root 2 M11 M22 minus P squared minus L squared. Okay, now don't copy this down. The important thing is to just notice that this is a conductance, so it has to be positive, right? Negative conductance doesn't exist physically. At least it's not a passive termination. So for this to exist, this term has to be bigger than this term. And that's exactly the condition that we talked about earlier under which a solution exists. Okay? Now because this condition is so important, we're going to spend some time talking about the condition for an optimal solution. All right, before I do that, is the notation clear on this page?
What's BL?
What's BL? Okay. BL is, so this is my 2-port, and I'm going to terminate it into JBL and GL. So it's just notation. And so what I found here is BL opt and GL opt. Okay? Thanks for asking that. Okay, so let's come back to this condition. I want this to be positive. In other words, I want 2M11 M22 minus P squared to be bigger than L squared. Right? So this has to be positive because this is really related to the real part of GL. Okay? And so rewriting this, you know, both sides are squared, so I can take square root of both sides. And I can define now a constant which has to be bigger than 1. So the condition for the solution to exist is that k has to be greater than 1. Okay? So up to here, this is just some wacky constant. We don't really know what it represents. We just know that it's related to having a real part, having a real load termination. Okay? Now what's interesting about k is actually called the stability factor. And it plays a really important role. So, in fact, these equations that we derive for the optimum load impedances can all be reformulated in terms of K. So, for instance, the optimum source, you may say, well, how did I get the optimum source? I only calculate the optimum load. Well, you calculate the optimum source by simply saying that ys star should equal to yn, or ys should equal to yn star. So you go through the algebra and you derive these equations. YL optimum almost has the same form. In fact, everything is nice and symmetric in these equations except the denominator. So you just have to remember one and then you can remember the other. And in fact, what you'll find is that the expression for the maximum transducer gain, which is also the maximum power gain, which is also the maximum available gain, takes a very nice form. It's y21 over y12 times k minus k squared minus 1 square root. And I recommend you commit this equation to memory. So I would say memorize this. It's a very, very nice equation. Okay, any questions about the notation? So we haven't done anything magic. All we've done is lots of algebra, and this problem is so important that after doing all this algebra you decide I should clean things up. And when you clean up the results, you say, oh, the results look nice and clean if I define this k factor. And this k factor, notice here it's plus, here it's minus. This k factor plays a very important role. And of course its name is a giveaway, dead giveaway. It's related to stability, unconditional stability of the two-port. Okay. All right, well, we can also, now that we have this general result, it's trivial to get the unilateral result. So if you plug in these equations, everything simplifies and you get the trivial case that you thought that we got without doing any algebra. But here's the expression for the maximum gain. If I look at this expression, y12 is equal to 0, so this blows up. But if I do the algebra carefully, the solution comes out to y21 squared divided by 4 times m11 m22. And m11 is the real part of the input y11, and this is the real part of y22. Okay, so this is just 4 real part of y11, real part of y22. So that long calculation we did to get the power gain of a MOSFET, we could just directly plug into this equation. y21 is gm, y22, the real part of y22 is just RO, real part of y11 is basically just a series to parallel transformation. Okay. Questions or comments? Okay. So let's one of the nice things about, well, one of the problems, if you go through, and I hinted at this last lecture, but I think you'll really get it when you try doing a homework assignment with one of these non-unilateral devices. You'll find that unilateral devices are kind of a pain. First of all, they tend to have stability problems. Okay, so I guess maybe I should save this discussion for after stability. Yeah, let's save that discussion for after stability. Okay, so we'll come back. Okay, so let's now focus on stability. We see this K factor is playing such an important role. First of all, I want to give you guys a good theoretical proof that stability is also related to the concept of a negative resistance. So the idea is, I like to call something stable if I can take an arbitrary black box, let's say it's an active network, and I terminate it into some load. Could be like a parallel RLC load. It could be anything. So this is a passive termination. And more importantly, by passive, meaning that this is bigger than 0. Okay? Bigger than or equal to 0. Could also equal to 0. And what I want is that under this condition, nothing should happen if this is stable. If I start observing oscillations here, then this is not stable. And what I'm going to show is that this is related to the real part of y in. If we can show that the real part of y in is bigger than 0, then this is stable. Okay? All right. So let's look at this problem for. So this is a one port, and it's actually quite trivial. I mean, I won't even prove it because it's so trivial for one port. So let's see what happens for a 2-port. So same condition on a 2-port. We want to terminate input port and output port into a real load. So again, we call this YS and YL, and we want this nothing to happen with this circuit. Well, we know that this circuit is described by the Y parameters. And in particular, V1 and V2 in this case are just related to the current. So if this is I1, V1 is minus I1 times divided by YS, and V2 is also minus I2 divided by YL. So I can substitute for I on the left-hand side, and if I plug this in, I get the following equation. I get Y11 plus YS, Y12, Y21, Y22 plus YL, V1, V2 is equal to 0. Okay? Now, I want, if there's actually a solution to this equation, that means the system is unstable. So I want the only solution to be the trivial solution, where V1 and V2 are also equal to 0. So we know from a simple linear algebra that that's satisfied if and only if the determinant of this is equal to 0. Right? So we want, in other words, we want the null space of this to only have the trivial solution V1, V2 equal to 0. So if I take the determinant of this matrix, it's simply Y11 plus YS times Y22 plus YL minus Y12, Y21, and we set this equal to 0. And if I now expand this out, I have YS, Y22, YL, Y11, YS, YL, Y11, Y22 minus Y12, Y21 equal to 0. And actually, let me do it a different way. This is too complicated. Let me just divide this equation by this term here. So I get Y22 plus YL minus Y12, Y21, Y11 plus YS equals 0. That's better. Because now you'll recognize the second term here. What's this? Exactly, this is Y out. So I have an equation that says YL plus Y out is equal to 0. If I do it the other way, if I divide by this term, I have an equation that says YS plus YN equals to 0. That makes sense? So what we've shown is that network is unstable at a particular frequency if this condition is satisfied. Let's say ys plus yn is equal to 0. So if the determinant of this matrix were not equal to 0, I misspoke earlier. If the determinant were not equal to 0, then it would be stable. Because it is equal to 0, I can have non-trivial solutions. So sorry about that. Sorry to confuse you guys. Okay. Now, this means that this condition is satisfied for both, has to be satisfied for both the real part and the imaginary part. So in particular, if this is the condition for the real part, the imaginary part is trivial, right? I can always make the imaginary part of this equal to 0 by picking the source imaginary part to be the negative of this part, right? That's trivial. But now we can see that since we have a passive termination, that implies that this is always positive, which implies that this term is negative. And using the same argument, it implies that this term is negative. So if we have a two-port that has any of these two conditions satisfied, let's call this A and B, so two-port is unstable if it satisfies either condition A or condition B. Okay? So let's now, when we have expressions for y in and y out, let's just plug in. So for general two-port, real part of y in is the real part of y11 minus y12, y21, yl plus y22, and this. So now we're going to look for stability. So the opposite is true. If it's bigger than 0, then it's stable, because then this equation can never be satisfied, right? If this is positive and this is positive, they can never sum to 0. Therefore, obviously, it's stable. And I can write a similar equation for real part of y out. Okay. And in particular, for a unilateral case, it's very simple. y12 is equal to 0, so these drop out, and so I just have real part y11 bigger than 0, real part y22 bigger than 0. So any unilateral two-port that has a real y11 greater than 0 and a real y22 greater than 0 is actually unconditionally stable, meaning that you can never put a source or load termination and cause oscillations to occur. Okay. Now, again, I'm going to skip some algebra and show, and just give you guys the result, is that just starting with these equations, you can show that these equations are equivalent to the following. So these two equations are equivalent to just one equation which says that k should be greater than 1. And if you look at this k, go back a couple of pages, you'll see that it's actually the same k factor that we found when we defined the condition for a solution to exist. So this is why earlier I asserted that the condition for a solution to exist is really related to stability. Okay? Questions? Comments? All right. So a couple of things to notice. This expression here applies for a two-port. It has nothing to do with the input port or the output port. This expression is invariant if I change ports 1 and 2, right? So it's a condition for the entire 2-port. That means that if port 1 becomes unstable, by definition, port 2 can also be unstable, and vice versa. So stability is a property of the entire 2-port, not just a property of one of the ports. Okay. So let's define absolute stability. So if I say a 2-port is absolutely stable, that means that it's stable for all passive load and source terminations. Now you might say that's very conservative, right? That means that if I have a 2-port, I can drive it with any source and any load, and it'll never oscillate if k is bigger than 1. It's absolutely stable. At least for all passive terminations, right? You might, so if you require this, if you're designing an amplifier and you say, I want my amplifier to be stable, you might say, I'm going to make sure that k is bigger than 1 at all frequencies. And someone else might come in and say, that's really, really restrictive, right? I mean, in real life, you know the load, you know the source. So why not just check k stability for particular source and load impedance? Why check stability for every possible load and source impedance, right? And you're right. So this is a very conservative because in practice the range of the load and source varies. So the idea is that if I'm designing an amplifier that I give to a customer and I say you can load it with anything you want, you can drive it with any source impedance you want, I guarantee it'll be stable. Then that means that k has to be bigger than 1. But then if I tell my customer, well, you know what, don't short the output. If you short the output, it's going to oscillate. Also, if you're driving it with a reactive source, yeah, it'll have problems. So if you're designing a general purpose amplifier that should work under all operating conditions, then you want this to be satisfied. On the other hand, if you're designing an amplifier that's embedded in a system where you control the environment, then this is too much. You might actually be able to do better if you work with an amplifier that doesn't satisfy this condition over all frequencies. Now don't get me wrong, you have to make sure that your amplifier is stable at the frequency that you're operating at, but it doesn't have to be absolutely stable. It could be stable for a certain range of source and load impedances. Okay? Is that confusing? Does that make sense? Questions? Well, what's also interesting is if I have something that's not stable, so let's say I have a 2-port that's unstable, and I want to stabilize it. What's a really easy way to stabilize this 2-port so that I make it unconditionally stable? Exactly, add positive conductance. So what I can do is, remember, instability means that if I look into here, the real part of y in is less than 0. If I just add a conductance so that the net, so I add here some g which is bigger than the absolute value of real part of y in, then the net conductance now looking into here is positive. So I've created a new 2-port that's unconditionally stable. Okay? And that's actually an important concept. It's going to let us define power gain for systems that are not unconditionally stable. Okay. Let me see. Okay, let me regroup my notes here. Yeah. Okay, so let me come back to this equation, this question of power gain in general. So what we found is that for a unilateral case, GT max exists if simply real part of y11 is bigger than 0 and real part of y22 is greater than 0. And if it's a physical transistor model, usually this is true. So you almost don't need to check this condition, but usually it's already satisfied. So for a unilateral amplifier, we can always find the maximum gain. On the other hand, if it's a bilateral amplifier, then we have to check K. If K is bigger than 1, stability factor is bigger than 1, then in fact GT max exists, and it's given by the ratio of y21 over y12 times K minus K squared minus 1. Okay? And if K is less than 1, GT max is then infinity, right? Because basically I can always build an oscillator. I can always find a source or load termination so that I get oscillations to occur at the output without providing an input, and that's infinite gain. But that's actually not very useful, because there are many situations where a transistor, let's say a transistor or an amplifier, is not unconditionally stable, but I still like to use it, right? And so with the intuition that we just got from the last slide, we can take our two-port, let's say K is less than 1, and add loss to the input and the output, so that we keep adding loss until we hit the boundary, K equals to 1. So we add enough loss until K is equal to 1. And then we actually have something from the external two-port here that looks unconditionally stable. And so then the expression GT max applies. So GT max in that case is y21 over y12 times K squared minus 1. But now K is equal to 1, this term's 0, this term's 1. So then it just breaks down to this expression, and we call this the maximum stable gain, or sometimes G maximum stable gain. And it's the maximum stable gain because we've stabilized our amplifier on purpose. Okay? The way to think about these loss terms is that I'm putting in enough resistance here to quench any oscillations that might occur otherwise. And now I have a nice stable two-port. So this is how I define the maximum gain for a device where K is less than 1. And the reason I like to define this is, you know, nobody likes to work with infinity, right? What's infinity, you know? So if I look at a particular device, let me take a transistor. So what's the maximum gain of a transistor? Let's say operated in common source configuration. Well, it turns out that at low frequency K is less than 1. That's because at low frequencies this device has lots of gain and it has feedback through CMU, so it's very easy to make it oscillate. At high frequencies though, what we call the knee frequency, there K tends to be bigger than 1. So if I were to plot the K factor versus frequency, it might look like, let's say this is 1, it might do something like that. Let's call this the knee frequency. So now if I plot the maximum gain, the maximum stable gain I can get from my device, so let's just call this G max, then up to a frequency of the knee frequency, it's unstable, so I have to use the expression GMSG, which is just simply y21 over y12. Beyond this knee frequency, though, it's unconditionally stable. There's a unique solution, and we observe a kink in the curve because now we're using y21, y12, k minus k squared minus 1. And of course these two meet at this point because this is by definition this expression for k equal to 1. And there'll be some frequency where this crosses 0 dB. That, of course, we define as the maximum frequency, or the Fmax of the device. Okay? So this very common way to characterize a transistor is you plot these various quantities, and this curve kind of represents, I shouldn't say kind of, it does represent the maximum gain you can get out of the device if you're just willing to change the source and load impedance, right? If I'm just willing to change the source and load impedance and to have a stable amplifier, this is the maximum gain I can possibly get. Okay? So this curve is the maximum gain attainable from two-port if you simply vary YS and YL. And of course they're passive. Okay? Yes?
At low frequency, the C mu should be an open circuit, right? Why there's a feedback?
Good question. It's because there is a feedback path present, and there's lots of gain in the device. So I can pick a termination so that the loop gain of the device becomes bigger than 1, right? So at very low frequency, your C mu is playing less role, but you have more gain in the device. Strictly at DC, you're right. The device is unilateral. Okay, very good point. You guys will have a homework assignment where you'll take a real device and you'll plot K as a function frequency and you'll plot these gains as a function frequency, and you'll get some intuition for it. Okay, so can I do better than this curve? Is it anybody think that we can maybe do better than this? Is this really the limit? Is this the best we could possibly do? What else can I do to try to maybe extract more gain out of my device? Okay, a wise guy would say use 2 devices in parallel, right? Okay, no, single device. Let's say we just use the same device. First, I was willing to drive it with any source or load impedance, and I find that this curve is a limitation. But what if I were willing to do something more? Use passive elements?
Are we allowed to use passive elements?
You mean active elements?
No, active. Possibly not allowed to use active elements.
No, you're allowed to use any passive elements, right?
So we try to unilateralize the...
Okay, yeah, that's right. So up to now, we haven't used feedback, right? We haven't allowed for the possibility of putting feedback around the amplifier. So the idea is, can we unilateralize the 2-port? That means that in addition, I'm just going to, let me draw it like this. So this is my input, this is my output. So now I'm not simply providing a source and load impedance like I was before, but I'm providing some kind of feedback. Okay? So if I'm willing, so this is basically passive. In other words, I'm not going to be putting any amplifiers in here. I'm just going to be putting L's, R's, C's, maybe transformers, but whatever I put in here is still passive. And the idea is that what I want to do is I want to create a new two-port, so this is now equivalent to a new two-port, which is unilateral. Okay? I haven't cheated, right? I'm not dissipating any more power than I was before. I still have a two-port. This is my bilateral two-port. And I'm now going to provide some feedback and make it a unilateral two-port. And the question is, if I do this, can I actually get more gain out of my device? Okay? Now, in this class, we're not going to discuss this unilateralization procedure. It's a lot of math. Do it in 217 or in 242. But we will look at a special case, because a special case is very simple. So the special case of unilateralization is called neutralization. So if I have a transistor, for instance, the only thing that's making this bilateral is C mu at low frequencies. How can I get rid of C mu? Yeah, I could just put an inductor in parallel here, right? At a single frequency, this inductor cancels out this capacitor, and the net effect is a unilateral transistor. So at one frequency, I've gotten rid of C mu. And that's very easy to do. Turns out that if you do that, you actually do get more gain out of your device. You can get a lot more gain out of your device. And yes, there's a question? With biasing? Sure, I mean, this is an AC schematic, so the way you would do it in reality is you'd use a big capacitor here. Okay? So if I unilateralize my device, or in this case neutralize, which is easier to say than unilateralize, if I neutralize my device, then I actually do end up getting more gain out of it. And there's a couple of neat ways of, this is one way of neutralizing a device, but there's a really cool way of doing it if you have differential circuits. So here's another way of looking at neutralization. So I have this C mu, and somehow I want to cancel out this current. So what if I could somehow take this voltage, multiply it by -1, and also feed it back, right? Well, if I could use a negative capacitor, that would do the trick, right? That would be nice, if I could use a negative capacitor. C mu, and then minus C mu, and the currents would nicely cancel out. But I can't use a negative capacitor. The next best thing I can do is take this voltage, invert it, and produce a current that balances this current. So now the net current going in is just the gate current. That makes sense, right? Well, in integrated circuits, there's a really easy way to do this. You just cross-couple your devices. So if I have a differential pair, for instance, then automatically I have the output voltage and its inverse available to me. So I can take this node here and connect a fake C mu, if you like, and I can take this node here and generate another fake C mu and connect it into here. So this cross-coupling will provide unilateralization for this device, or neutralization. Okay? All right, any questions? Does that make sense to everybody? And there's other ways to do it. We won't go into details. You can use transformers to provide phase inversion, for instance. You could use center-tapped inductors. So there's lots of tricks that you can play. Okay. coming back to this curve, what you find is that in the case that your device is unstable, if you unilateralize it, then it becomes stable by definition, right? Because you're getting rid of the feedback. And then you can use this formula again for maximum gain of a unilateral amplifier, and you'll find that you can actually get more gain. So this is the what we call the U, or the unilateral gain. Another way to unilateralize a device is, for instance, use a cascode. So again, for a cascode, the problem with CMU, and if I basically I have a, without the cascode, I have a large voltage here which generates a large current. If I now buffer this, so this is a large voltage, and this can be a relatively small voltage, that minimizes the effect of CMU. So this device tends to be much more stable than a single device. And in fact, if I plot the GMSG of this device, I find it has quite a bit more gain than a single device, for a couple of reasons. One, it's unilateralized. Two, it has higher output impedance. And so these two reasons together make this device a much higher power gain device. But you would expect that because it's actually a two-stage amplifier, right? So it should have more power gain. Okay, I think that's all I want to say about stability. Actually, let me say a few more things. How about, so if we do this more detailed analysis, in other words, if we use a more complicated transistor model, for instance, can we zoom in on this first figure here? So this is a more complete model of a FET, and it tries to include all the loss mechanisms in the device. And the reason we're doing this is because when you actually, really sit down and think about how much power you can extract from a device, it all comes down to the losses in the device. I mean, partly it's the omega T of the device, right? We saw that even in the simple amplifier. But the other terms really came out to depend on the inherent resistances in the device. So if we can minimize these resistances in the device, we can maximize how much power gain we can get out of the device. So for instance, what are those resistances? Well, we've spent a lot of time talking about this gate resistance already. We also talked about this channel resistance, but unfortunately we also have to worry about the source and drain resistances. And as I commented early on in this class, in a modern device we have to make very shallow source and drain junctions so that we don't have short channel effects, and that means higher resistances in the sources and the drains. And so you can bet that these are also going to contribute to the loss in the device. The other form of loss that you have to always live with is the substrate resistance. No matter what you do, you're building your device on a conductive substrate, and the body node is physically isolated from your device by some of these resistors. And even though your source and drain junction are reverse bias, they don't conduct DC current, they certainly can conduct AC current through these substrate capacitances. So at high frequencies we also tend to inject currents into the substrate which have to flow through these physical resistors, which also leads to loss in the device. So if you really do a more careful analysis of what the maximum gain you can get out of this device, you know that it's going to depend on all these resistors. Well, one of the graduate students here, Chin-Don, analyzed a simpler version of this and came out with a nice expression for Fmax. Let's zoom in on this equation here. So Chin found that for a modern CMOS device, you can express Fmax as approximately the Ft of the technology, which again, Ft doesn't depend on loss, right? It just depends on the bias point, the GM of the device, and CGS of the device. And then terms that depend just more or less on loss. So here we have the gate resistance, we have the channel resistance, and we have the source resistance. This is also the GDS of the device related to the output impedance of the device, so this is 1 over RO. And then here we have terms that are related to the GM of the device, the overlap capacitance related to the total capacitance, and the gate resistance. So this is the maximum operation frequency that we can get from the device. And as a circuit designer, when we lay out our device, we can try to minimize some terms. We've already talked about we can minimize RG, for instance. But at some point, we are stuck with certain process parameters. For instance, we called this mu early on, the ratio of C gate to drain to CGG. This is something that's getting worse and worse in a modern process. We also can control the channel resistance by putting more current in our device.